So hi everyone, I'm Haochen Wang. Along with me, we have Tomasz Czajkowski and Ehsan Amiri. We are three people from Huawei's BiSheng compiler team, and it's a compiler developed from the LLVM project. Today we're going to be presenting an anatomy of optimized matrix multiplication on AArch64. So a little bit of background and motivation. There are many mature techniques already for matrix multiplication. For example, there's tiling and packing. Of course, you can use vectorization and same instructions. And there's another technique called outer product expansion, which we will explain in this presentation as well. But the issue is the effectiveness of these kind of techniques don't really scale well over a wide range of matrix sizes. There are some techniques that are only very effective at small sizes, and there are other techniques that are only really effective at large sizes. So today in our presentation, we will present our work on choosing the appropriate techniques for the appropriate sizes and how to best combine these techniques together. So what is matrix multiplication? It's basically this picture on the right. Each entry in the output matrix is an inner product between a row of the first input matrix and a column of the second input matrix. And matrix multiplication is widely used in many algorithms. It's used in solvers of important engineering equations. It's used in training machine learning models. Most of the time when you're training machine learning models, you're just waiting for matrices to multiply. Therefore, the performance of matrix multiplication is really the bottleneck of the performance of a lot of modern algorithms. And the matrix multiplication we'll be looking at is to multiply the two source matrices A and B and add them to some already existing matrix C. So it's an accumulate. We'll be talking about double precision floating point matrices just to make our presentation more concrete. And we will be talking about single threaded algorithms. So we ignore the discussion of parallelization in this talk. By the end of this talk, you guys should be able to understand which techniques we use to achieve this high performance. So we are testing on a machine where the theoretical maximum for a double precision single thread is 10.4 gigaflops. GFLOPs stand for giga floating point operations per second. And the theoretical maximum for the machine is 10.4. And we can get quite consistent 9.9 all the way up to a very large matrix. And here we're only showing square matrix multiplication, or MM. We're only showing square MM performance measurements because it's really hard to tabulate performance result numbers for rectangular matrices because there are like 3 size parameters and the table would be very messy. But rectangular matrix multiplications of similar sizes will have similar performance as their square siblings. So why is matrix multiplication so slow? So over here, we have the usual procedure for doing a matrix multiplication. The first entry is the 0th entry is the inner product between the 0th row of the first matrix and the 0th column of the second matrix. And then how do you do that? You load that row, you load that column, and you take an inner product and you write that, or rather you add it to whatever was originally there. And then you advance to the next entry, you load this row again, you load this column, this new column, you take your inner product. But in this procedure, the first row, the 0th row actually, the 0th row of A is being loaded twice. And that's unnecessary reloads. And for a matrix of size n, this unnecessary reload will happen n times. We can do a very quick back of the envelope estimate. Each item in the output matrix needs to be calls for 2n loads of the source matrices. And there are n squared items in the output matrix. So that's 2n times n squared, that's 2n cubed, or order n cubed loads from each matrix. Another issue of why MM is so slow is because one of the source matrices will break cache locality. Our matrices in this talk today will be assumed to be stored in column major order, which means the array double star little a is going, as you advance one step in the array, you advance one entry down a column in the source matrix. So 0, 1, 2 is going down the column. If you're at the end of a column and you advance one step in an array, you go to the next, you wrap around to the next column. And as you can see in column major storage, if we're loading an entire row of matrix A, every time you load another element, you're jumping across a lot of addresses, which means it breaks cache locality, causing for slow performance. Okay, so we have to counter these two factors. So let's first look at countering reloads. It's fairly obvious that the more registers you have, the fewer reloads you have to do, because the actual math, the actual inner product, the multiplies and adds will be done on registers. And if you only imagine an architecture with only one register, each time you do a piece of math, you have to load another new thing into that register for the next piece of math, and nothing can be reused. So the more register you have, the fewer reloads you have to do. And of course, we want to exploit all the available registers, and we don't want anyone sitting idle on the side. In this talk, we'll be focusing on AArch64. It has 32 vector registers for double precision, and each can hold 2 doubles. And you can access these vector registers however you like. You can access them in Neon. Here's the documentation for Neon intrinsics. You can access them through direct LLVM instructions. But in any case, these are the resources we have. And the important realization for countering reloads is that if the matrix is small enough, then all the matrix elements can be held inside these registers. And that size turns out to be 4x4. We'll see why in due time. But for a 4x4 matrix, every matrix element can fit in these vector registers entirely, which means after that first load, you don't have to evict anything from the registers. You can just use them, and there are no need for reloads at all. For a kind of medium size, you do need reloads into the vector registers, as we have more matrix elements and some reloads are bound to happen. So the problem is there any way to avoid some of these necessary reloads? But for the medium size, cache locality isn't really that bad yet, so we don't have to consider cache explicitly. But as we increase to an even larger size, like 1,000 times 1,000 and higher, cache locality starts to degrade drastically, and explicit measures like toweling and packing are needed to counter cache non-locality. So let's start with the easy one. Let's start with the 4x4 small matrix multiplication who fits entirely in registers. Okay, so remember we have 32 vector registers on AArch64, 2 doubles each. And here's the allocation scheme for the registers. We use 8 registers for A. Remember, we're in column major order, so when we load into a vector registry, we're loading 2 continuous guys in a column. We have 8 of these registers for A. We have 8 of these registers for C. And for the matrix B, we need 16 registers, where in each register, we duplicate one of the elements into both lengths. The reason we do that is because when we're taking the inner product, so in this example, we just focus on one of them. The C00, C10 is the inner product between this row from A and this column of B. When we're taking the inner product, we need to multiply both lengths of A by the same constant in B. So how does the procedure look like? We first duplicate these elements. These are pseudo instructions on AArch64. We first duplicate these B elements into the vector registers. Both of B32D now holds B00, both lengths of this. And then we do the appropriate loads from A and C. There are 16 loads necessary. We load A00, A10 to V0, and so on and so forth. So now at this point, after the duplicate and the loads, every matrix element is loaded into the vector registers only once. And then we just do the appropriate multiply adds. For example, here we're multiplying V0, which holds A00 and A10, so it's this guy. We're multiplying it with V30, which is a register whose both lengths hold B00. We multiply them, both of A00 and A10 will be multiplied with B00, which is what this inner product is supposed to do. And we just simply add it to V10, which holds the resultant C00, C10 in the resultant matrix. And then after this FMLA, we just advance to the next multiply add. And there's a bunch of them. You just have to do them all. But when you're doing them, you don't really load anything again. So these are just pure arithmetic instructions, which are faster than loads by a bunch. And after the FMLAs are done, we just store the C register back into their respective places. This is written in a pseudo AArch64 assembly, but Of course, you can do an LLVM IR version of this. You also have load vectors, store vectors, and you also have FMAs for double precisions. And to accomplish this this duplicate instruction in LLVM IR, you might need to do a little bit of vector surgery from like extract element or shuffle vector, but it's of course possible. Okay, so that was the easy part, but now we're advancing to a somewhat more complicated problem, the medium-sized matrix multiplication, and some reloads are bound to happen here, and we want to see how we can avoid some of them. The crucial technique for avoiding some of these reloads is called outer product expansion, or OPE. So what is outer product expansion? In this little figure, that shows matrix multiplication, each of these elements can be just a scalar, but they can also represent blocks because matrix multiplication can be done in arbitrary blocks as long as the blocks themselves being multiplied are of legal dimensions. So outer product expansion is nothing more than a special blocking scheme. The first source matrix, A, as to speak, is blocked into columns, and the second source matrix is blocked into rows. So effectively, the first source matrix only has one row with each entry in that row being a column. Similarly, the second source matrix only has one column, but with each entry of that column being a row. And because it's a row multiplied by a column that is just one inner product, you just multiply each of the elements. So that is the first element to be multiplied. You multiply the second element, and then you add them together. So this is what outer product is. And within that little multiplication of one element, which is called a single outer product, this is a very special thing because this is a matrix product. And as matrix products go, the mnth element in the product matrix is the inner product between the nth row of A and nth column of B. But the nth row of A and nth column of B, both of them just has one number. So it's just a single garden variety scalar multiplication. So this one is the product, the garden variety scalar product between this one and this one. This one is the product between these two, and this one is the product between these two. Similarly for the other entries in the product matrix. So each entry in the product matrix is just a product of their corresponding row and column. You can imagine them being headers in the source matrices. The beauty of this approach is that it inherently supports loop invariant code motion. Because every single element in the first matrix in a column is to be multiplied by the same scalar from the B matrix, you can load this scalar outside the innermost loop. So when you're looping through the row from B, you can load this underscore B outside the innermost loop. You can load this one into this B, and then as you're looping down this column, multiply this already loaded thing with each of these ones to produce each of these ones in the product. And then you just go to the next one in the B row, and you go to the next one in the B row. So now everything in B is loaded outside of the innermost loop, which means the number of loads is decreased by an order of n. Originally, there are n cubed loads from B, so now it only has n squared loads, which is the minimum number of loads needed because there are n squared elements in B. And what about A? Because the loads in A are still happening in the innermost loop where you loop down this column, so it still has n cubed loads, so there's some extra work that needs to be done there. But at this point, A has an order cubed loads and B has an order squared loads. How about loads from C? So how does the outer product look like when you're actually doing it? After you do the first outer product, and then you do the second outer product. That is basically the procedure. But inside an outer product, you have to load the C in the innermost loop because you're accumulating to them one by one. There's nothing common in the C matrix that can be factored out. So it's still in the innermost loop, which means there's still a total of n cubed loads from C. So a summary of outer product. A and C still has n cubed loads, but B has n squared loads. So we now want to try further reducing A and C loads. And the art is, of course, to use our super fast loads everything only once previous 4x4 microcore. So now let's imagine this m by 4 times 4 by n outer product and just focus on the upper left corner, which is the product of these two little 4x4 corners. And in the naive outer product, you have n cubed, which is 4 cubed, 64 loads from A, n cubed, 64 loads from C, and n squared, 4 squared, 16 loads from B. That tallies up to 144 loads for this 16 writes in this little corner. But if we do this 4x4 matrix multiplication with our 4x4 microcore that loads everything only once, that's only 16 loads from A because there are 16 elements, 16 loads from B and 16 loads from C. And that tallies up to only a total of 48 loads for our little upper left corner of 16 writes. So that's 96 loads fewer. That's a lot of loads fewer. And you can see the benefit of our microcore in action. And of course, because every 4x4 in this column of A is to be multiplied by the same 4x4 in B, you can also lift them outside the innermost loop, and you can load them before you go into a loop that loops down the column of A, just like the scalar case before. And here's a procedure for how we would do that, including register allocation. And before we go into the innermost loop, remember B takes up 16 registers. Each of these guys takes its own register. So that leaves us with another 16 registers available for A and C in the innermost loop. Remember, AArch64 has 32 vector registers for this purpose. And as you are going down the column of A for a 4x4, A takes 8 registers and C takes 8 registers. So that fully uses the 16 registers available for the innermost loop. And then you just call the 4x4 microcore and do it in the previously mentioned way. In this fashion, you are utilizing loop invariant co-motion, you're loading B only once, and you're exploiting fully out of the 32 vector registers. And of course, in the innermost loop, you can unroll it, you can do prefetch, you can do all of your favorite textbook optimization techniques. So this sounds like a very good version of matrix multiplication. So we tested the performance of it, and something surprising showed up. So as you increase the matrix size, the performance actually degrades pretty quickly. It's very good for 128 size. It's very good for a small size. It's almost as good as the theoretical maximum of 10.4, but it degrades very quickly. So the takeaway is this can be used as a 128 by 128 matrix multiplication macrocore. And of course, we are curious as to why the performance degrades. And that brings us to the last piece, the large full matrix multiplication at large sizes. So the problem is, when we're doing the first version, the technique in the first version, here's one of the microcores that needs to be done. After we load A00, A10, the next load we want to do is A01, A11. But this load jumps across addresses. Remember, our matrices were in column major order. So if you're after loading this blue register, you load this green register. But if the matrix size is 128, this jump in addresses is size 128, which is not that bad. It's acceptable. But if your matrix is very large, like maybe 2048, then this jump in addresses is going to be 2048, which has very, very bad caching because it has very poor spatial locality. That's why in the first version, we have a very fast degrading performance. So to counter this, we of course want to do the entire matrix multiplication in 128 by 128 blocks, but specifically we want 3 temporary arrays that are themselves only 128 by 128 sized, because then in these arrays, we don't have cache problems. And then after we pack the 128 by 128 blocks into these temporary arrays, we simply use the first version, which were 10 gigaflops on these arrays. So how should we schedule these 128 by 128 macro cores? In this figure, in this little illustration, each cell now is not a scalar. It represents a 128 by 128 macrocore. And when we're counting loads, and I talk about a load, it refers to an entire 128 by 128 load. So of course, you can just do it the naive way, the traditional way. You just do single inner products. So you load a 128 times matrix size row from A, you load a single column from B, and you multiply them to get the single element in C, a single 128 by 128 macrocore element in C, and you just do this for every single element in C. And that tallies up to 576 loads, 8 loads from here, 64 loads from here per 1/8 of the C writes. But what if we do things in tiles? What if we do things in tiles? We can pack this 4 times 8, really 4 times 128 times 8 times 128, but let's call it 4 times 8. We can pack this 4 times 8 upper half of matrix A into a temporary array called double A pack. Similarly, we pack these 32, 8 times 4, 32 macrocores into another temporary array called double B pack. And then we multiply these two arrays together to get the upper left, to get the upper left corner of the target matrix. If we do this in this fashion, because they're packed, you load them only once. So there's 32 loads from A, 32 loads from B per a quarter, I guess, a quarter of C. That tallies up to only 256 loads, which brings us to a tally of 320 fewer loads. So tiling can save us a lot of loads as well. So this is how we should go about this problem. And just a little naming convention. The tile size is actually this height of the A row pack and the width of the B column pack. In this example, a tile size is, of course, 512 because there are 4 macrocore lanes that are size of 128. Each tile has 4 of these macrocore sized row and column panels. And when you're doing the inner product of the two tiles, you simply divide up the 4 macrocore sized lanes from each of the packs, each of the tiles, and you just do 4 times 4, which equals 16 corresponding necessary inner products. But there's a final issue remaining. If we just pack them in the naive way, we're faced with an extra load from the tiles packing array. We call them A pack and B pack. And remember, we had to call the first version on 128 by 128 arrays for cache friendliness, but there's an extra load needed from the packing array to the temporary arrays. To illustrate this problem, let's imagine a small scale toy example. The tile size is 4, the macrocore size is 2 by 2, and each tile thus has 2 rows or columns of macrocore sized panels. And let's color code these guys. A tile is color coded by a light orange color. A macrocore sized panel within a tile is given a medium orange color, and a 2 by 2 macrocore itself is given a dark orange color. So here's the, let's take the 8 by 8 matrix multiplication as an example. In this figure now, each cell is a scalar. It's not a 128 by 128 anymore because we're doing a small scale example. These are tiles. These two tiles, again, produce the upper left corner of the target. This tile is called double A pack. Its size is 4 times 8. This tile is double B pack. Its size is 8 times 4, and you just multiply them together. Here's a macrocore sized row and a macrocore sized column, and there are 2 for each tile, so you have to do 4 inner products of macrocore sized. And here's the upper left corner of these. Here's the first of these that you have to do. And when you're doing them, you want to load each of these 2 by 2 macrocores into their corresponding arrays that are only 2 by 2 sized. And you just do their inner product, you iterate through this macrocore sized lane of the tile. And you add them together to produce this upper left corner of the upper left corner. All right, but there's an issue. There's an issue. So when we're packing the upper half of the first matrix into double star APAC as an array, what if we just pack it in simple column major order? That means the 0th element of APAC is the upper left corner element here. The first element of APAC is the element immediately below it. The second element of APAC is the element in the matrix immediately below APAC 1. APAC 3 is immediately below APAC 2. You wrap around column here, go down here, wrap around the column here, go down here, wrap around and go down, and so on and so forth. The same for B. You start at the upper left element of B, it's BPAC 0. You go down a column, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you just pack the tile arrays APAC and BPAC in naive column major order. And what if you do that? And now when you want to actually multiply the macrocores together, the 2x2 macrocores together, cur A and cur B, you have to load these elements in the tiling array into our temporary macrocore arrays, because the elements that needs to be multiplied in the tiling array are not together in contiguous segments of the memory. They are not together in contiguous segments in the pack. If you just call the first version of cur A and cur B while placing cur A at APAC 0 and placing cur B at BPAC 0, it will actually do matrix multiplication on this APAC 0, 1, 2, 3 as a column and BPAC 0, 1, 2, 3 as a column. But these two things are not the appropriate matrices to be multiplied. Instead, if we pack the tiling arrays in this zigzag fashion, then we can avoid this problem. After APAC, below APAC 1, we don't pack the item below it in the source matrix, but we pack this item. And APAC 3 is given by this item. These numbers are not matrix elements, they're addresses within the packing array. And same for B, we wrap around the packing here inside the macrocore instead of going down a column naively. In this fashion, if you simply position cur A at the pointer cur A at APAC 0, the pointer cur B at BPAC 0, and you call the first version, automatically you're multiplying these two macrocore matrices. To go to the next macrocore, you simply increment the pointer by the macrocore size, which is 2x2 in its example. So now cur A points to 4. It originally points to 0. 0 plus 4, it's this macrocore. 0 plus 4 in B is this macrocore. And now, if you just call the first version again, it automatically multiplies the next necessary macrocore. So there are no loads needed from the packing array to the macrocore temporary arrays. Let's do a quick summary of our algorithm. So first, we want to tile A into row tiles, and we want to pack the A rows in the zigzag fashion. We also want to tile B into column tiles, again in the zigzag fashion. And within a tile, we want to do tile size over macrocore size squared inner products that are themselves macrocore sized. And for an inner product of macrocore sized, because we're doing zigzag packing, we can iterate through the inner product by simply incrementing the pointers and not doing any extra loads. And within a 128-128 macrocore matrix multiplication, we use the first version, which was the outer product plus the 4x4 microcore. Okay, so that was the presentation, and thanks for everyone listening, and thanks to Excel that made these otherwise really annoying graphs possible. Okay, we'll take questions now.
Yeah, thank you for the presentation. Let me see if we have any questions. Okay, I don't see any questions yet from here. Yeah. So I have one question. Are there any like recent research papers where these ideas are also like given in more detail, or this was purely from your side, like experimental, and you figured out the optimizations?
So we haven't written this into a paper yet. So there's no formal publication. We simply wanted to present this algorithm at a conference. So yeah, but there are other, these techniques themselves are fairly mature. And at the outset, we did say that the idea of our presentation is to showcase how to use these techniques for different sizes on a size hierarchy, because some techniques aren't effective for small sizes. For example, toweling is not very good for small sizes. So that was the goal of our presentation. But if you want to read some papers regarding these techniques themselves, we have a reference slide right here.
Okay, awesome. Thank you.